Good morning. All right, we're going to pick up where we left off in section 2.4. We've got a couple more examples there, then we'll get into 2.5 today. Just a reminder that the 2.1 to 2.4 homework is due by midnight tonight. So like I said, you should have already had pretty much everything you needed to complete that one. I do want to do these last two examples just to show you a couple of things, but you could have at least been working on those anyway. So make sure you get that done by midnight tonight. And then once we get into 2.5, then obviously you can go ahead and start on the next homework assignment that starts with the 2.5 stuff. Let me know as you have questions. Stop by in student hours if you need to. But any questions, comments, concerns before we get started today now? All right, so let's take a look here at example 3. So this time, instead of giving us an actual function, we're given a table of values. Okay, so those are the values we're actually going to use here to solve these problems. So it says the table in the margin gives the outdoor temperatures observed by a science student on a spring day. First, it says to draw the graph. We're not going to worry about that. We just want to worry about finding the average rate of change of the temperature between each of the following times. Okay, so for part A, we're looking at the average rate of change in our temperature between 8 a.m. and 9 a.m. So the way we're going to do this is we're going to think of the first column here as our x values, and then we're going to think of the other column as our f of x. So give me just a minute. See if I can get this back up there. There we go. All right, so this is going to be the x column. Sorry, my pen's not writing. Give me 1 second. There we go. All right, so this column is going to be our x, and this column is going to be our f of x. All right, now once we've got that, now we're going to use that f of b minus f of a over b minus a formula that we looked at last time, right? So remember, average rate of change is f of b minus f of a all over b minus a. Okay, so in this case, what is our a value going to be for part A? Okay, so instead of using 40, right, because that's actually going to represent an f of x value, that's going to go in the numerator, let's just figure out what a and b are first, right? So what would the a value be this time? The 8 a.m., right? So 8 o'clock is going to be the a value, which means that 9 o'clock is going to be the b value, right? So those are like the x values, those are the times, okay, so those are going to represent the a and the b. So now when I actually set this up, I'm looking for f of 9 minus f of 8 all over 9 minus 8. Now this time, instead of having to actually substitute into a function to get the f of 9 and f of 8, we can just look at the table to find those values. So what is f of 9 going to be this time? That's the 40, right? So we have 40 minus, and then what is f of 8? That's the 38. Good. And we're going to put that over 9 minus 8, which is just 1. And so now when I subtract and simplify that, what am I going to get? Just 2, right? So 2 over 1, which just gives us 2. Now, we need to keep in mind what our units are going to be on a problem like this. Okay, so what does that 2 actually represent this time? Okay, so the numerator here represents degrees Fahrenheit, but the denominator represents what? Okay, so it is a temperature change. So if we want the, oh, all right, good. So it's a temperature change over time. In this case, our temperature is measured in degrees Fahrenheit. Our time was measured in hours. So this is going to represent 2 degrees Fahrenheit per hour. Okay, so that's what I would be looking for units on something like this, right? Because we know the numerator represents the degrees Fahrenheit, the denominator represents the hours. So this is now 2 degrees Fahrenheit per hour, meaning that our temperature rose by 2 degrees for every hour between 8 o'clock and 9 o'clock. Any questions about that one now? All right, let's look at part B. So what's our A value this time? One o'clock, right? So we're going to do 1 is that, and then that means that the B value has to be the 3. Remember, B is always the bigger value. So now when I set this one up, I'm looking at f of 3 minus f of 1 all over 3 minus 1. Okay, so again, I'm going to use the table now to find the f of x values. What would f of 3 be this time? Good, 67. What's our f of 1 going to be? That's 62. When I subtract down here, I get 2. So now we're going to simplify that. So what's that going to give us? Okay, 5 in the numerator, right? So 5 over 2. Or if you want to write it as a decimal, what would 5 over 2 be? $2.5, right? Either one of those would be fine. I think in this context, right, the decimal actually kind of makes a little more sense. Okay, so this is 2.5 what? Okay, good. Degrees Fahrenheit per hour. And so basically, again, this is a positive value, meaning we rose by 2.5 degrees Fahrenheit for every hour between the hours of 1 o'clock and 3 o'clock. Any questions on that one now? All right, so now the last one, again, our A value is going to be the smaller value, B is going to be the bigger value. So we're looking for f of 7 minus f of 4 all over 7 minus 4. So what's f of 7 going to give us this time? 51, good. Minus f of 4 is going to be what? 64. And that goes over 7 minus 4, which is 3. And then what's 51 minus 64? It's going to be a negative 13, right? So negative 13 over 3. Okay. Or if you prefer the decimal, what would that decimal be? Negative 4.3 repeating, right? And again, our units are going to be the same. So it's going to be degrees Fahrenheit per hour. Now this time, notice we got a negative rate of change. So that just means that our temperature is decreasing by 4.3 degrees Fahrenheit for every hour between 4 o'clock and 7 o'clock. Any questions on any of those now? So whenever you're given a table of values, you're asked to find an average rate of change. Same formula we've been using, right? It's just that now we don't actually have to substitute it in. We can just pull those values straight from the table now. All right, example 4. Okay, so now we've got this function 3x minus 5. We want to find the average rate of change between each of these points. Okay, so again, same formula, right? This time we have our a value is 0, b value is 1. We're looking for f of 1 minus f of 0 over 1 minus 0. Now, how are we going to find f of 1 this time? So you could graph it, right? Or we could just substitute that value into the function that's given, right? So, and that's what I'm going to do here is I'm just going to plug the 1 into that function. We're going to have 3 times 1 minus 5. So that part right there gives us f of 1 minus. And now if I want to find f of 0, I'm going to do the same thing. 3 times 0 minus 5 is going to give us f of 0. And now my denominator, 1 minus 0, that's just going to be a 1. So now we just need to simplify what we've got up there. So what's 3 times 1 minus 5 going to be? It's negative 2 minus, and then 3 times 0 minus 5 would be what? Negative 5. Good. Over 1, right, we can kind of drop that because anything over 1 is going to be itself. What's negative 2 minus a negative 5 now? Right, that becomes addition, and so this becomes a positive 3. And so our average rate of change between 0 and 1 now should be positive 3. So just don't forget, right, subtracting a negative becomes addition, so negative 2 plus 5 is 3. Any questions on that one? All right, now the next one, our a value is the smaller value, b is the bigger. And so now we're going to substitute that in. We're going to have f of 7 minus f of 3 all over 7 minus 3. Right, so just like the previous one, we're just going to substitute those values into our function. So we're going to have 3 times 7 minus 5, and then minus 3 times 3 minus 5, all over 7 minus 3, which is 4. All right, so now what is 3 times 7 minus 5 going to give us? Good. 21 minus 5 is 16. Minus, and then 3 times 3 minus 5 would be what? Good. So 16 minus 4 all over 4. So then if I simplify that now, what's 16 minus 4 divided by 4? Good, right? So we get 12 over 4, and that just gives us 3. Any questions on B now? All right, last one. Okay, so A and A plus H. So A is the A value, A plus H is the B value. This time we're looking for f of A plus H minus f of A all over A plus H minus A. Now, when I do f of A plus H, what's that going to look like for this function? Good, right? So we're just substituting a plus h for the x. So we have 3 times a plus h minus 5. That takes care of that piece. Minus. And then what's f of a going to be? Just 3a minus 5, right? Because we're just plugging an a in for x. We get 3a minus 5. All over, what's a plus h minus a going to be? Just h, right? Because a minus a cancels. So we're left with just an h now. Now we need to simplify our numerator. So I'm going to go ahead and distribute here first. So that's going to give us 3a plus 3h minus 5. Then I'm going to distribute this minus to both of my terms in the brackets down here. So that's going to give us a minus 3a and a plus 5 all over h. All right, now, if I combine like terms in the numerator, what are we going to get? Just 3h, right? Because we have a positive 3a and a negative 3a. Those are going to cancel. The negative 5 and the positive 5 are going to cancel. And so now we're left with 3h over h. So what's 3h over h? Just 3, right? Because now the h's cancel out, and I'm left with 3. Now, I want you to look at all of our answers here for A, B, and C. What do you notice? Why are they all 3? Why would my average rate of change in all of these situations be 3? Yeah, if you look at this, what type of function did we have? So 3x minus 5 is what kind of function? It's linear, right? And we know a linear function has a consistent slope, which means it has a consistent rate of change. So no matter which 2 points I choose on that line, my slope is always going to be the same. So my rate of change is always going to be the same. So anytime you start with a linear function, you don't actually have to do all this work, because any 2 points that I choose now, it's just whatever the slope is of that line, right? So my rate of change of that line is always 3. So no matter what A and B values I choose, I'm always going to get 3 here. Yeah. So just pay attention to what type of function you're dealing with, right? Because it can save you some work. If you recognize it's linear, you know the slope is the rate of change no matter what. Okay? Any questions on that one now? You mean like any other types of function history? Yeah, there are no other ones where it's that simple, right? Because every other function would have a variable rate of change, right? Parabolas aren't going to have the same slope, depending on where you pick a point, that slope would look different. Same thing with like an x cubed function, same thing with square root functions, right? So linear functions are the only type where you can just look at the slope like that. Any other questions there? But fun fact, if you do take calculus, there are some really quick shortcuts to find rates of change if you do go on to take calculus. Okay, so with some of these, right, the work that we have to do here is a lot more cumbersome than what you would actually have to do in calculus once you learn some shortcuts. Okay. Derivatives is actually where the rates of change would come in. Integrals would be the inverse operation of that, right? So the opposite of taking a derivative would be finding an integral. All right. 2.5, linear functions and models. Okay, so what we're going to look at in this section is how do we actually model certain real-world situations using linear functions, right? And then what can we then use those for? Okay, so here we go. All right, so linear functions, right? We've already talked about the fact that a linear equation is y equals mx plus b. Now we're just saying that that is actually a function also because it will pass the vertical line test. So f of x equals mx plus b, where m is your slope, b is your y-intercept. Okay, that is the graph of a linear function, which is a line. Again, that's the same form that we looked at back in chapter 1. All right, so here the question is, we want to figure out, are each of these linear functions or not? Okay, so the first one here, we've got f of x equals 2 plus 3x. So the question is, can we get that into that form, mx plus b? So what do you think? Yeah, we can, right? So all I'd have to do in this case, right, addition is commutative. I can switch this order. So I could rewrite this as 3x plus 2. That is our mx plus b form. Therefore, this one is a linear function. So that's all we're doing on each one of these, seeing if we can rewrite it in that form, and if we can, then we know it's linear. So what about g of x? What can we do to that one? Distribute, right? So if I distribute now my 3, that's going to give us 3 minus 6x. And then could I get that into that mx plus b form? Yeah, right. Again, just switch the order of the terms here. Make sure the negative stays with the 6. So that's a negative 6x and a positive 3. And so again, that's in that mx plus b form. Therefore, we would say this one is also linear. Any questions on that one? Okay. What about h of x? What would I need to do first? Distribute, right? So if I distribute this time, I'm going to get x times 4 is 4x. X times 3x is plus 3x squared. Okay. So now, can we get that into that mx plus b form? We can't, right? So this time we actually have an x squared term. We can't get it in mx plus b form. So this one is not linear. Any questions on that one? Okay, so look at the last one now. So 1 minus 5x over 4. Is there anything we could do to that to get it into that mx plus b form? What could we do? So we can't just multiply by 4, right? Because that would actually change the value of the function. But we can take each one of those and put them over 4, right? So since I only have a single term in the denominator, I can put each of my terms from the numerator over 4. We're going to have 1 over 4 minus 5x over 4. Now, looking at that, could I get that into my mx plus b form? Exactly, right? I can just switch the order like I did before. So that's just going to give us 5/4 x, sorry, negative 5/4 x, and then plus 1/4. That is mx plus b form, so this one would also be linear. Right, so in this case, especially like g of x and k of x here, they don't necessarily look linear to begin with, right? So always look to see, can I simplify it somehow and get it into that mx plus b form? Because if I can, then I know I still have a linear function there. Any questions on any of those now? All right, skip example 2. slope and rate of change. Okay, so for the linear function f of x equals mx plus b, the slope of the graph of f and the rate of change of f are both equal to m. Okay, so whenever you see this term, rate of change, and this kind of goes back to that last example from the previous section, right? The slope of that line was 3, and the average rate of change, no matter what 2 points I chose, was also 3. So whenever you see slope and rate of change for a linear equation, they mean the same thing. Okay, they're both equal to m, which is the coefficient of x. So yes and no. The reason we have to be careful here and say that this works for linear equations is because the slope is consistent for all linear equations. When you start talking about other types of functions, that there is not really a slope of a parabola, right? There's not a slope of a square root function. And so when you're talking about those rates of change, it's not exactly a slope. It is, right? Because you're choosing 2 points and putting a line on it, right? But the slope itself only refers to the line, not the function itself. Okay, and so that's why we just have to be careful how we define this, right? We're only saying this works for linear functions because really only lines have slopes to begin with. Okay, but other functions can still have rates of change even though they don't have a slope. So that's why we have to say for linear functions, they're the same thing. Does that make sense? Okay. So yeah, so again, in the context of a linear function now, whenever you see rate of change, same thing as slope. All right, so a dam is built on a river to create a reservoir. The water level f of t in that reservoir at time t is given by the function f of t equals 4.5t plus 28. T in this case represents the number of years since the dam was constructed. F of t is going to be measured in feet. So f of t now represents the water level measured in feet, and t is a time that's measured in years since that dam was built. Now, I'm going to assume that we can put this into a graphing calculator or Desmos, right? You would just put 4.5x plus 28, right? So when you graph it, right, your calculator is only going to do things in terms of x, so just change the t to an x and you can graph it that way, right? So I'm not going to bother with the sketching of the graph. What I do want to answer are these other two questions, though. Okay, so what would the slope of that graph be in this case? 4.5, right? So the coefficient of x in this case, that's your m value. So m equals 4.5. Now, the second question, or the last question here, at what rate is the water level in the reservoir changing? So how would you describe the rate at which the water level is changing now? Good, right? So in this case, right, remember the slope and the rate of change for a linear function are the same thing. So in this case, 4.5 is our rate of change, and now we just have to put our units on it. Well, we said that the 4.5 times t is measured in years. We know that our water level is measured in feet. This is going to be 4.5 feet per year. That's what that slope or rate of change represents in the context of this problem. Now, is that water level rising or falling at that rate now? It's rising, right? And we know that because we have a positive rate of change or a positive slope. So I would probably also say in this case that we are rising at 4.5 feet per year, just to make sure it's clear that that is a positive rate of change. Any questions on how we got that? No, as long as you have it as a positive 4.5, right, I would still give you credit. But just keep in mind, right, contextually, understanding because it's positive, it's going up. And if it was negative, it would actually be going down. Those are important things to keep in mind. Okay. And there are some problems in the homework where you have to choose which of these statements describes the rate of change. And so then you would have to understand, oh yeah, it is going up, not going down, right? Because there's probably a choice for each of those. Okay, so just pay attention to that. If you put a plus beside it, it's fine, right? You don't have to, right? Because it's understood to be positive, but if you do, it's not wrong. Any other questions there? All right. So example 4, water is being pumped into a swimming pool at a rate of 5 gallons per minute. Initially, the pool contains 200 gallons of water. So we need to find a linear function that models the volume of the water in the pool at some time t, and then we'll answer the other question once we have our model. Okay, so let's think about how we can get a linear model here to represent this situation. Any thoughts on what that linear model might look like, or anything that we know about that linear model? Okay, good. So we know it's going to be in the form y equals mx plus b, right? Because we know we're looking at a linear model, so it has to be in this form. Now the question is, do we know the slope and do we know the y-intercept, right? Looking at all the information here, the slope is going to be 5, right? Because that's the 5 gallons per minute, so that gives us our m value. And then there's initially 200 gallons of water in that pool. That's going to give us our starting point. That's the y-intercept. So 200 is actually the b value this time. And now in this case, we want to make sure we're using the variables they give us, right? So they've asked us to use v to represent volume, t to represent time. So then what would our linear function look like in terms of v and t then? Okay, so v equals, because that's our volume, and then we're going to have 5 times t, good, plus 200. So since it's 5 gallons per minute, where t represents the number of minutes, we got 5t, and then plus the 200, that's our y-intercept, that's our starting point. And if I do that, that should give me the volume of water in the pool now. Any questions on the setup for that one now? Okay, now the question is, if the pool has a capacity of 600 gallons, how long does it take to completely fill the pool? How are we going to figure that out? Good. We're going to let 600 be our volume, and we're going to solve for t now. This is going to be 600 equals 5t plus 200. 600 is the volume. That's the volume of the whole pool. We want to know how long it's going to take to get there, so we need to know t. So then what would you do first to solve that equation? Subtract the 200. Good. So that's going to give us 400 equals t. And then we can divide by the 5. So what's 400 by 5? Should be 80. Good. So 80. And then we need our units, right? Okay. And so Alexander's got it there. This time was measured in minutes. So it would take 80 minutes to completely fill the pool this time. Any questions on any of that now? All right. Number 5. Okay, so now we have a figure here. They give us the picture. Placed a staircase in a coordinate plane with the origin at the bottom left corner. The red line here is the edge of a trim board on that staircase. We want to find a linear function h that models the height of the trim board above the floor. And once we have that linear function, then we can answer the question down at the bottom. So we're using h to represent our linear function this time. So what are we going to need to know? We need the slope first, right? And we also need the y-intercept. So let's find the slope. So how am I going to find slope for that line? Okay, we're actually going to use our slope formula, right? So remember, back in chapter 1, y2 minus y1 over x2 minus x1, that's our slope formula. Well, they give us 2 points here, right? So we can let this be our x2, y2. Let this one be the x1 and y1. And it doesn't matter which one's which, right? Okay, because if you switch them up, you'll still get the same answer. If I substitute in there now, I'm going to start with my y's. So 32 minus 16 over, and then 36 minus 12. So if I simplify that now, what's that going to give us? Two-thirds, right? Because the top here is going to be 16. Denominator is going to be 24. 8 goes into both of those numbers. 8 goes into 16 2 times. 8 goes into 24 3 times. So now we know our slope is 2/3. Any questions about how we found the slope of that line now? All right, now the other thing we said we needed was the y-intercept. Do we have the y-intercept here? It's 8, right? Because we can look at our graph, crosses the y-axis right there at 8. So now we know that b equals 8. So now what's our linear function going to look like? We know the slope and we know the y-intercept. Good. So 2/3 x. And then we have plus 8 for our y-intercept. And so you could technically call this like h of x if you wanted to, where x represents the horizontal distance of that staircase. Any questions on finding that linear function now? Okay, now the question is, if the space available to build a staircase is 11 feet wide, we want to know how high that staircase would reach. So now we're saying basically if you had 11 feet of depth, right, along the X here to build this staircase, how high would it reach? So what am I going to need to do first? Okay, close. Here's what we have to be careful of, though. What are the units along our x-axis right now? It's inches, right? So notice down here, this is in inches. We were given feet. So like Destry said, we need to convert first, right? How would I convert from feet to inches? You're going to multiply by 12, right? Now, if you're unsure of when to multiply, when to divide, what the conversions are, that kind of thing, one thing I always do is I can multiply by a conversion factor. That way it's always multiplication. And then I just figure out, what am I trying to get rid of? What am I trying to get to? Well, in this case, I'm trying to get rid of my feet. So I'm going to put feet on the bottom so they cancel out. And I'm trying to end up with inches. So I'm going to put inches on top. How many inches are in a foot? 12, right? So I'm going to put 12 inches in the numerator for every 1 foot in the denominator. Now my feet are going to cancel out, so I'm left with inches, and now I'm going to multiply straight across. Well, 11 times 12 here is going to give us 132 inches. And again, that always takes care of whether you need to multiply or divide, because a lot of times that's the confusing part, right? To go from one unit to another. Am I multiplying by 12? Am I dividing by 12? But if you set it up this way, it's always multiplication, and you just need to set up your units so that the things cancel out that you want to cancel out, and you end up with the units that you want to end up with. All right, now that we have 132 inches, now we can substitute that into our function, right? So we're looking for h of 132. So we've got 2/3 times 132 plus 8. And so what's that going to give us? Should be 96. Good. And so that's going to be 96 what? Inches. Perfect. So the height of our staircase in that case would be 96 inches. Now, if you wanted to, we could convert back into feet, right? Just so you have it in the same units that we started with, the 11 feet. I'm going to take the 96 this time. This time it's in inches, right? But again, I'm always multiplying. And then I just have to decide. So I'm going to move it over here so I can write it. So 96 inches times, what units am I trying to cancel out this time? Inches, right? So that means the inches are going to go on the bottom. I'm trying to convert back into feet, so feet are going to go on top. Now my conversion's the same, right? It's 12 inches for every 1 foot, but this time the 12 inches goes on the bottom, the 1 foot goes on the top. And my inches are going to cancel, and I'm going to be left with feet. So when I multiply this time, I have 96 in the numerator, I have 12 in the denominator. So now I'm actually taking 96 and dividing by 12. Well, what's 96 over 12 going to give us? 8, right? So this is 8 feet would be the height of our staircase. Again, yeah, if you left it at 96 inches on a test or something, I'm perfectly fine with that. But just in case there's a multiple choice problem or something in the homework and you're trying to match it up, that's how you would convert back into feet if you needed to. Any questions on that one now? All right, so last example from this section, see how far we can get through this one. So John and Mary are driving westward along I-76 at constant speeds. So the graph here at the bottom, right, shows the distance y in miles that they have traveled from Philadelphia at time x, which is measured in hours. Okay, so just keep that in mind, that this is in hours. Where x equals 0 corresponds to noon, and noon, John has already traveled 150 miles, right? So notice here that his y-intercept is up here at 150. So starting from noon, he's already gone 150 miles, okay? All right, so we got the same graph there. Our first question is, at what speeds are John and Mary traveling? Right, and then we'll talk about who's traveling faster once we know what their speeds actually are. So how are we going to find their actual speeds here? Okay, so let's think about what we know about this graph, right? What does the y-axis represent? What are the units of the y-axis? So looking back here, right, what does the y-axis tell us? It's miles, right? So that's their distance that's measured in miles here. Right? So we've got the y-axis up here, going to be measured in miles. And then what does the x-axis tell us? The number of hours that have passed, right? So this is measured in hours. So if I want speed now, what would I need to do with my y and x values? So if y is the miles, x is the hours. So not point slope, but just find the slope, right? Because if you think about it, miles per hour would be a speed. So I really just need to divide the number of miles traveled by the number of hours that have elapsed, and that'll give us our speed in miles per hour. Well, that's the same thing as finding a slope, because the difference in the y values over the distance, or the difference in the x values, is going to give us the slope, which is now the speed. So for John, if I want to know his speed, I just need to find the slope of his line. Now, there's a couple of points that are already plotted on there, right? So we just need to find the ordered pairs of those, and then we can find the slope. What would this first point on John's line right here that's plotted, what would that point be? Looks like 250, right? So 2 would be the x, 250 would be the y. And then his other point up here would be what? Good. That's going to be 350. So now we're just going to use our slope formula to find the slope, or the speed between those points. So that's going to give us 350 minus 250 over 4 minus 2. And so what's 350 minus 250? Good. So we have 100 over 4 minus 2 is 2. And so what's that going to give us then? 50, right? And then what are the units going to be this time? It's miles per hour, right? Because remember, the y values were the miles, x values were the hours. We have miles per hour. And now let's go ahead and get Mary's speed, and that's probably the last thing we'll be able to do. We'll have to come back and finish this one up tomorrow. So again, I'm looking for my slope. So again, I need the points. I'm going to go ahead and label those. This first one's at 150. Her other point is at 300. So now substituting in here, we're going to get 300 minus 150 over 4 minus 2. It's going to be 150 over 2. And so what's her speed going to be? .75 miles per hour. Okay. Now, real quick, how does that show up on the graph, right? Because we can see in this case that Mary's speed is 75 miles per hour, his is only 50. We know she's traveling faster. How does that show up graphically? Could we have been able to tell that without even doing the calculations that she's going faster than he is? It's steeper, right? So just looking at the steepness of the line now, right, since the slope represents the speed, whoever's line is steeper tells you who's going faster, right? So we can easily look at the graph and see that, all right? So again, we'll pick up with the other questions tomorrow and finish that up and then move into the next section. Again, don't forget the 2.1 to 2.4 homework is due by midnight tonight, so make sure you finish that up. Send me questions if you've got them. Otherwise, I will see you tomorrow. Have a great afternoon.